Yeah, so today episode is about preparing the data to be synced into a storage. So advanced analytics could be done. You can analyze your data, review your data, infer information from it, but also use it together with AI. So we have done 2 or 3 episodes before, which this will follow up on them. So we're going to use the same repo, and so you can later see all the changes in that GitHub repo. But so for those of you who haven't joined before, I'm Tomas Neubauer. I'm CTO and co-founder of Quix, and I specialize in working with the sensor data. I worked my whole career with the sensor data from cars, trucks, aircrafts, F1 cars, simulators, wind tunnel machines, etc. So let's go back to where we stopped last time. So if you remember, we have a 3D printer machine with sensor data, and we getting this data from over MQTT topic or topics rather. Now we have shown and play with last time how to normalize the data from the MQTT format to something more consumable. And this is what we're gonna do today. And I'm gonna show you how it's better one format over the other when you actually land your data in the database. So let's inspect first the data straight from the MQTT. So this is actually unsyncable because the payload is just a value. So that would not really work. We're gonna have to do some key normalization into the payload, so we actually get some columns in our payload, and that is what this data normalization service is doing. Now, if you remember last time we did both things in the same service, I had to split it for this episode so I can show you actually the difference. So output of this service is something which is still very similar to what MQTT sends, except the topic tree structure is being transformed into columns in a payload. So instead of having a complicated key, which was representing the topic structure in MQTT, now here we have that in a payload. So now we have a timestamp, machine, sensor ID, and value. So let's sync this to a database and let's play with that. And I'm gonna show you where it starts to get unpractical. But this format is also very powerful because it does not suffer from some drawbacks that you will get in the other formats we're gonna use. So that's why it's important that none of the formats I'm gonna show you today is a server bullet. So let's deploy here a thing. Um, so I'm gonna use today a QuickLake database. So QuickLake is basically a data lake over S3 with a metadata catalog where we're gonna save the data. So here I'm gonna use first the sensor data. I'm gonna get the bucket. So I'm gonna use the S3 bucket called Quix test bucket. So I'm gonna paste it here. I'm gonna put it into the iceberg folder. It's actually not native iceberg, but in this folder, I already have a lot of data, so I'm using it. The table name, let's call this a sensor data. Let's follow the name of that. Now it's the time to decide how you partition your database. Now this is very important because when you're creating your schema for your database and when you thinking how this is going to be consumed, that has to go hand to hand with how you structure your indexes. So if you're using something like an influx, it's about the tags. if you use something like a relation database, you're gonna have to think about the indexes, what's gonna be the cluster index, what is not, etc. If you're using data lakes, like here we're gonna have the S3 Hive folders with the packet files. You need to determine the Hive columns because those will give you a fast partition pruning, in other words, a fast queries. So here, if we duplicate this tab to remind ourselves what columns we have in the topic we're gonna sing, let's just quickly uh, refresh our memory. So this topic looks like this. You have machine and sensor ID. Those two can be probably quite often in a where clause, okay? So let's use them to split it. The sensor ID as a folder is questionable. You can think of in some use cases where you would just keep the machine, but for now, let's do that. So I'm gonna put here a machine and the sensor ID. And that's about it. Now we have to put our catalog address. So I'm gonna go to QuickLake project and I'm gonna give it the URL here. And that's about it. Yeah, maybe I'm just gonna add a bit of in a batch size. So let's see. Yeah, and we have to give it also the secrets, which I have pre-populated, so we don't do that here on the call. And then the last thing is the region. So I believe we are here in West Europe. Yes, we are. So let's put it here. Amazing. So that seems that worked, and you can see it's already pushing data directly to S3, and it's also registered the table into a catalog. So that means that if I go here to the QuickLake, we have here the table now. Now you can see that our structure look like this. So we have a machine, which is printer one, and then we have a subfolders for each sensor. Now, if we just select this, we're gonna see that under value, we have all the sensors, and then here under sensor ID, we have what sensor that is. If I just put a bit more here, and maybe instead of style, let me just get here the sum of the columns so we don't completely. So we have the timestamp, then we have the machine, and then we have the sensor ID, and then we have the value. Maybe 1,000 is a bit more, too much, but yeah. So if I scroll down now, you will see eventually it's only so far the bed temperature. Maybe if I do 2,000 to get other sensors, maybe a bit more lucky. Okay, so let's get here a fun speed if we're gonna get something. Yeah, so now you see there's a fan speed, and you can, for example, say, okay, I want a fan speed, or let's say I want the bed temperature. Bed temperature is quite high resolution, so let's get maybe the infill density. Okay. Now that would give us two columns of the three. And again, you see that I get the data, and because most of the stuff here is indexed is actually quite fast. However, the problem is, what if I want to do, for example, downsampling, and I want to have the font speed and infill density together? I would have to do quite complicated join, and on top of the join, I would have to do downsampling. It's going to be slower, and also it will really put the complication to the user, which is somebody who wants to work with data, not get a PhD in SQL. So that's where this gets to its limit. The second problem is, what if I want, for example, to get the data where I want to get a fan speed when bed temperature is in some region. It's the same problem. I cross-referencing the columns, and it's not going to work. So this is where, if we go back to our pipeline, here we're gonna use this data transposition, which we basically implemented together last time. And if we go to this topic, here we have a particular output frequency with all parameters in it. So now we can get each sensor as a column, which is basically the second schema I wanted to show you today. So let's go here and let's deploy existing application. Let's get the sync. And here, we're not gonna use the sensor ID as the folder anymore. Doesn't make sense, we don't have it. We're gonna call this a sensor table this time. And let's just get all the data. Or maybe not. And yeah, that's about it. And let's call this a QuickLake sensor table sync. Good. So this will sync to a different folder and in a different format. So if we go to our S3 bucket and do a refresh, we can see that here we already have the sensor data, something I already showed you. Now, while this is being deployed, let me just show you how it actually looks like. So here we have the sensor, different sensors. So if we go to bed temperature and we go to the actual files and we download the file, and now I'm gonna reshare my whole screen in a second to show you how that will look like. So if I stop sharing and share again, there we are. So here I have that packet file loaded, and you recognize this. This is the same thing we were doing before. So I can do here a TSMS sensor ID value, and maybe just get 100. There we are. So that is working. And be careful, you don't get, for example, machine here, because that is in a hive folder structure, so it's not duplicated. Anyway, let's go back to the browser and let's check the progress with our second table. So good. So going back here and checking this, you see it's already written a data. So if I refresh this, we have another table called sensor table with the machine. So I'm gonna put it here from sensor table. There we are. I believe I have done a mistake and I'm using the wrong topic. So let me stop this and let me drop this table and recreate it because it's a wrong one. So I'm gonna drop this table. Cool. And here the input topic has to be sensor table. Otherwise we will be looking to the same thing. That would be not great. Okay, so now this is gonna read the data from the topic as it did now. And now it's writing to S3 and it's already registered the table. So if I do a refresh here, amazing. And I can already run the query. So now you see that we have the different columns in our query. It's better to use a limit, not to get your browser completely destroyed. Amazing. So now what we're gonna do is first just print a couple of columns and clean the result so we can continue. So if we get the time, then we get machine, and then fun temperature and bad temperature, if I'm correctly remembering the columns, band temperature and fan speed. Yeah. Let's get that. And yeah, and bed temperature. Sorry. Let's copy it so we don't do any typo. Amazing. So now we have all sensors sharing timestamps. And that's going to be super powerful. And let me show you why. So the first thing we can do here is, for example, say, all right, I'm gonna look at this data for a bigger time period, and I'm gonna downsample it, aggregate the information to bigger time intervals, to and then, for example, show min, max, mean on one graph. So instead of this, I'm gonna replace it with a typical time bucketing. Let's call this a time, just time, not time bucket. And except seconds, let's give it a minute. And then the machine gonna remain. And then let's get, for now, let's just get the bed temperature. And let's get a mean for now. And see what's gonna happen. And we have to do, of course, go by time and the machine, so we don't mix the machine data between each other. And probably if we want to print this to a plot, we want to order it by time. And that's about it. Good. But what is actually each row represents? Well, it represents a bucket of data. So we can test that by saying count, and every time series database will give you that. But here is the beauty, because we have this schema. It's super simple. I can do it like this. I don't have to do any joins. It's just like that. So now you see that 600 rows is behind each row here. Well, that means I can do something like this. Well, that could be quite cool if we plot it, don't we? And this is where we get to basically a final important bit. You want to create a schema and you want to use an architecture, data architecture, which is transparent. So, you are able to discover what you have in your storage because you need to kind of always remember that one person is going to be ingesting data into the system, another might be doing the data architecture, some data engineer, and then the actual domain expert, some mechanical engineer, or somebody who really understands data, they might have a lack of information, knowledge transfer between them. And as a result, that end user might not know that we have all these sensors and we have all these machines and all these tests. So for that reason, the discoverability is an important issue to solve. The second one is to get to the tools they use. So definitely one is a Grafana. So to set up the schema, which will be easy to use in Grafana, and it's discoverable by Grafana, which means that the autocomplete drop downs and all of that is working. So for example, they will see the columns in Grafana, not by typing them, but by using the UI of Grafana. The second one is an easy way to get data into something like a Jupyter notebook. So I have prepared here, that's why you saw from the beginning, the Marimo, which is a really cool tool. So here we see we're getting a select from the same storage and we plotting it like this. So we have a fan speed and bed temperature all in one query being printed here. But what we can do is open this locally in edit mode, which is I'm just gonna do that right now. Cool, so this is the same thing. And I'm gonna replace this SQL query with the query I just created, okay? So here, let's copy this, accept the limit. We don't need the limit anymore. We want to show all the data. Like that. And look at that. So, of course, the middle one is the mean. The max is above, the min is above, below. So you can see that over the last, yeah, you see the timestamps. There's not much in this yet, but over the course of this time, um, the temperature fluctuate between 65 and 85 roughly. And now what you can do is just push this Marimo file, which I'm gonna do right now, because the beauty of this Marimo to a normal Jupyter notebook is that it's very well versioned in Git. So as a result, I can go here and you don't see that, but I'm just basically committing the main PI into Git. And I'm going to show you here in Quix that if you go inside the service, here, that is the analysis, the cells that the domain expert will build with this UI. And so now here I'm gonna have the change. So this will get a new version. And as a result, if we go here, as you can see, the Git change was notified. And now it's rebuilding. So if we go again to the version control, it takes some time to push. Now you see the change, and that is now being deployed. And when this is published, and released, it will show us the different waveform. So to summarize what we have to do with schema, we have to get a schema which is defensive to any data quality, which is the first one. That schema is not sensitive to order of data. It's not sensitive to replace, reprocessing, because it's stateless schema. What I mean by stateless schema is there is no stateful processing involved in saving that schema into the database. So that's why you probably want that schema to have anyway, even if you're not gonna give it to domain experts and end users in your company. Because at the end of the day, it will be the most reliable if anything goes wrong. And so you want that. However, it's less practical for the advanced analytics. That's why you have the second schema where you do the transposition, which we started the last episode, and you can do more than we did today. You can also, for example, downsample data to different buckets. So you have tables which are pre-downsampled, because the downsampling on time series databases is fast, but it's not ultimately instant. So as a result, you would reach that time series database limits, and then you can switch between different tables and make your query faster. You can do more. You can do things like data quality checks, and you can, for example, measure the signal quality, for example. So you know that you should receive 60 rows per bucket if you have 100% of the data. So if you have less than 60 values per bucket, you can consider that as a drop in quality of data. And you can then, have a scalar value representing that. But anyway, this is deployed version of our just review. All of this is going to be in a GitHub repo, so feel free to use it and have a play with it. And yeah, hopefully see you next time. And as always, if you have any questions, reach out to us on our Slack. We are happy to, answer anything.